Well, welcome everyone back to Thinking Space. Thank you all for coming today. Before I begin, as usual, I'd just like to do an acknowledgement to the traditional owners of the land we're on today, so the Gadigal people of the Eora Nation. I'd also like to acknowledge the traditional owner of the land that any of our Zoom attendees are on, and pay my respects to both the elders past, present, and emerging, and extend that respect to any Aboriginal people who might be here with us today. I'd just like to advise that today we'll be recording the Thinking Space session onto our YouTube channel, and it will be available to rewatch later. But without further ado, I'd like to present our presenter for today, so Professor Josh Cinner, who we are very fortunate to have here at the School of Geosciences. And just a little introduction, he's a quantitative social scientist who studies human-environmental interactions on tropical coasts. He has a background in geography with a passion in sustainability-focused research at the intersection of social science and ecology. And from the bio, he's worked all across the world, which has had impacts on policy and conservation. So today he'll be talking to us about the Thriving Research Hub. Thank you.
Thank you very much. So I thought I'd start today a little bit differently. I kind of got inspired by Duncan Watts's book, Everything's Obvious Once You Already Know the Answer. And what he talks about in that book is our kind of system one is Danny Kahneman talked about. Our system one brain is great at filling in information. And once we actually know the answer, we have this incredible ability to convince ourselves we knew the answer all along. And why are we bothering with this research? And this can really actually undermine the importance of things, particularly in social sciences, because we're all experts in people, because we are people. So what I thought I'd do is kind of one of the papers we currently got in review. I might kind of start out with having you guys give your best guess, which is really what percentage of fish in the ocean is attributable to management or conservation. Now, don't worry, if you don't work in this field at all, you're actually no less informed than the world's experts on this particular answer. We actually don't know. We've been asking the wrong questions about this. And so I thought it'd be really fun. You guys can go ahead and put your answers in, and they should kind of come up as we're going.
What does it mean?
Yeah, that's another question.
So what does what mean?
Sorry, what does attributable mean?
Oh, right. And so, well, I'll get there. So what I'm gonna do is, how much less fish would there be in the absence of conservation? Right. So if we could think about, so what I'm going to use is use counterfactual thinking to frame this question. So how much less fish would there be, if there was that? And I'm going to give you guys the answers in a specific unit, which is kilograms per hectare, right? That's the amount of fish in a given area of reef. And I'm going to specifically talk about coral reef fisheries, but I don't think it really matters. I think, it's probably generally applicable to any kind of type of fishery. We're probably within a little bit. So anyway, we've got a great range of answers from 0 all the way almost up to 100. Maybe we can kind of circle back to that to see how it looks in a little bit. Okay, we're getting some more in there. All right, cool. Oh yeah, a few more. All right, well, we'll take a look. Okay, so I'm a geographer, and I study human environment interactions from kind of local scales, where I work with coastal communities and have these multi-decadal partnerships with villages in Papua New Guinea, right up to these kind of global scale studies that I've been leading. I primarily use coral reefs as a focal study for my interests. Coral reefs are, they're not only amazing in their own right, they're these incredibly beautiful systems. They're convenient ones to study because they respond on timescales that are relevant to studies. Human impacts, they can actually be impacted quite quickly, and they can actually recover in timeframes in which you can study them. So they're quite cool like that. But the main reason for me is that fishermen are just crazy, right? Fishermen are like, they almost predictably, actually unpredictably, according to kind of rational behavior theory, right? So they almost always do the opposite of what you would expect. When you look at their risk-seeking behavior compared to the general population, they're off on kind of one extreme, and so they're actually looking for windfalls rather than average gains, and so this drives economists a bit crazy, and that's really fun to work with. So I got my start working on coral reefs kind of serendipitously. In the mid-90s, me and my ponytail signed up for the Peace Corps, and I got stationed in Jamaica, and I got stationed in a coral reef marine park, and there I kind of fell in love with reefs themselves, but also really began to appreciate the complexity of the problems confronting them and how many of the solutions were really inhibited by social and cultural and historical problems. And the great example in Jamaica was that fishing in Jamaica is one of the few jobs where unskilled labor can be their own boss, right? And in the context of a post-slavery society, being your own boss is worth a lot more than just the economics of a job. So when they were constantly presented with opportunities to go work for lumpy white people in resorts, they weren't actually interested in doing it. And it would drive the consultants, the overpaid consultants that came down to help our park, absolutely bonkers. And I thought this was just extraordinary. So I furthered my studies by working with an anthropologist named Richard Polnack, who's the kind of one of the godfathers of maritime anthropology at the University of Rhode Island. I then moved to James Cook University to do my PhD. Some colleagues politely put it that I became an ingrown hair and stayed a bit too long. And so I ended up becoming a center investigator and program leader for the ARC Center of Excellence for Coral Reef Studies. I ran a really intensive field-based program there. I'd work all over the Western Indian Ocean, parts of the Pacific, and in other systems too, like in Chile. I'd often be gone 150 to 200 days a year doing field work. Things had mellowed out a little bit, particularly since having kids, but that was kind of the basis of what I did. Was a very intensive field-based program. And I've recently moved operations here to begin the Thriving Oceans Research Hub. And the goal here is really to deliver solutions-oriented interdisciplinary research that increases the sustainability and resilience of our ocean and supports the people that depend on them. So to me, thriving isn't just about the ecosystems, it's about thriving coastal livelihoods as well. I'm very interested in linking social science with not only ecology, but also fisheries science. These three fields have kind of been at loggerheads, particularly dealing with coral reef fisheries issues for a long time. And so this is an idea, my idea is to kind of bring them together in this global community of practice. We've just started assembling our team. So the first official hire is Thomas over there. Welcome, Thomas. We're so happy to have you on board. He didn't come far. He came over from physics, so we were very happy to poach him. It was a big win. We've got a master's a philosophy student, Adit. He's going to remain at JCU. He's working on looking at the sustainability of Indonesian coral reef fisheries. We've got a visiting student, PhD student from China, Yi. We've got two research assistants that are remotely based. We've got a database consultant, Ian, who used to be one of my postdocs, and he's now working part-time for an international conservation organization that's developing the data platform we're using. So he's working part-time for them, and he's a consultant for the project a couple of days a week to help us get all of our data on track. We've got probably 4 or 5 PhD students we'll have as part of the project. We've just sent out an offer to Natalie, the first one, and we're really excited. I'm sure she's going to accept. She's from Columbia and studies reef fish ecology, so she's going to fit right in. And I was able to put out offers to 7 postdocs this week. One of them's in the room. Say hi to Bess. We're hoping she says yes. No pressure, but everyone's looking at you. And one of the real goals is one of the key goals is to establish a interdisciplinary working group hub, right? We're going to hold a working group series here. I want this to be a kind of central place globally when people are thinking about ocean sustainability issues. So we'll have a working group here. This is to conduct deep interdisciplinary research and really work closely with end users. We'll probably do one at One Tree Island. Next year, we'll have one at Lancaster University in the UK. One of our project partners will host it. So there's kind of 2 main pillars of today's talk. And the first is, what I would kind of think of as maybe the main event of what we're trying to go for. And this is to identify the most resilient reefs and learn lessons about building resilience from those to kind of inform positive change in other places. That's gonna, in this case, we're essentially looking for the unknown unknowns, and we don't know what we'll find, and it's kind of a long shot, and it's gonna take about 5 years to do. So along the way, we've got to have a bunch of side hustles, and so we've got to actually kind of do our daily business. And so we're going to be trying to answer fundamental questions about conservation kind of along the way as this bigger project is unfolding. So let's talk a little bit about the main event first. As scientists, we often are trained and we spend most of our career focusing on averages and trends, right? And that's really important for discerning the signal from the noise. But today I'm going to highlight an alternative approach, which is focused on locating and learning from outliers, and in particular, outliers that are doing well despite difficult conditions, right? So by their very nature, right, outliers, they deviate from our expectations, and consequently, they can provide really novel insights into confronting really complex problems where conventional solutions fail. So this type of kind of positive deviance analysis has been used in fields such as business and health and human development to uncover local actions and government systems that work in the context of widespread failure. It's also used a lot in medicine. So in medicine, they have an approach to systematically studying extremely resilient patients referred to as exceptional responders. Now, exceptional responders may, for example, have a remarkable recovery from a drug treatment, right, where the majority of people in the experimental trial may not have any effects at all. There may be a subset of patients that do remarkably well, right? So the studying exceptional responders has led to major medical breakthroughs. For example, the treatment of HIV/AIDS was radically transformed when genomic sequencing of an exceptional responder revealed a mutation that prevented the virus from infiltrating his white blood cells, despite the fact that he'd been repeatedly exposed to the virus, right? They were able to mimic this mutation and create a whole new drug treatment to help treat HIV/AIDS. So the exceptional responders approach is now a major focal point in the medical community, particularly in oncology. And there's exceptional responder centers in Harvard, actually here in Sydney, the Garvan Center, and throughout Europe as well. And so my laureate project proposed using this framework of exploring exceptional responders to locate the most resilient reefs, uncover their enabling conditions, and see how these could be used to inform positive change. Now, this is the kind of natural step from a previous project I worked on. We're approaching 10 years ago now, 2016, which identified what we called bright spots. These were reefs that had more biomass, that's the amount of fish on a reef, more biomass than we would have expected given the conditions they were exposed to, right? These weren't the most pristine reefs. These were the reefs that are doing well despite difficult conditions, right? Now, one of the things, with time we can reflect on our own work, and I think that's important. One of the real kind of things that came out, particularly when we did a deep dive in one particular bright spot, was we revealed how these conditions can really fluctuate dynamically over time. And so this really revealed to me the importance of looking at things rather than this kind of snapshot in time, to looking at things dynamically, right? And so one of the advantages of doing this kind of what I would call this proof of concept was that a lot of people really fell in love with this approach, and people were writing to me and saying, if you're going to follow up on this, I've got tons of data from here. You missed this country. I've got lots of data. Turns out there was about 10 times more data than we originally started with. 26,000 sites from 68 different countries, right? We've got tons of people so keen to help collaborate and work with us on this. And so we've got about 1,000 sites entered so far. There's a lot of work to do to get the rest of those entered, but that's the first challenge to the project, I guess. So the first stage is really to locate the most resilient reefs. And to do so, we're going to explore how key social, ecological, and environmental drivers shape key fisheries resilience metrics, right? And I think this is really where I'm most excited about being here in geosciences, right? There's such a variety of perspectives here, and particularly ones that, coming just from the coral reef community there that I really hadn't considered. And I think there's a really great opportunity to collaborate with people across geosciences and really think through what are some of the key drivers from your field. And I'm particularly excited, some of the team that we've put put out offers to are experts in causal modeling. So I'm very excited about kind of going beyond just correlative models and looking at some of these causal models and really better understanding what drives resilience. We'll then use a predictive model to generate expected trends as counterfactuals, and then look at deviations, how our observed values deviate from these counterfactuals, and use this to classify whether something's an exceptional responder, whether it's a poor responder, or whether it's an average responder. Now, my original idea was to kind of use the 2016 global marine heat wave, right? It was a mass coral bleaching event. And I was going to use that as the focal event, but we may actually have to rethink things, because last week NOAA declared another global mass bleaching event happening right now. And so we may actually have to decide, do we actually have enough time to really look at recovery from that last one? And so this is one of the first things that the team's going to have to do, is really decide, whether that's still going to be viable. And maybe we need to get a new Twitter or X hashtag, which is climate change is inconvenience for scientists, right? Inconveniencing scientists, because people aren't responding to it being an existential threat for their livelihoods, and they think we're in on it because it's good for us to get funding, but maybe we need to kind of share that side of it, that it's actually not very good for scientists. So the second stage is really exploring how enabling conditions could inform policies for positive change in other locations. And so in the medical literature, what they do is they systematically identify unusual genome, transcriptome, and metabolome features among exceptional responders, right? And so, so what I'm going to do is look for social ecological analogs of these, right? So the genome is essentially the blueprint or the code for doing things. And so I'm going to look at how which elements of the social ecological context can enable or inhibit resilience, right? The transcriptome is the processes which enable the traits coded in the genome, right, to express themselves. So the social ecological kind of analog of that are the processes that enable people to convert the context into resilience. And the metabolome are the set of molecules that are that kind of fuel metabolic reactions. And so the analog of that are the kind of elements that enable resilience, or what social scientists call the adaptive capacity. So I'm going to assemble, my team of researchers, and we're going to go out and do targeted research. Once we've identified these exceptional responders, we're going to look for the 5 exceptional, the 5 average, and the 5 poor responders, and compare to see whether there's common enabling conditions among these different classifications of responders. All right, so that's the kind of main event. Again, as I mentioned, we're looking for the kind of unknown unknowns. That's going to take 5 years. So we've got a lot of stuff that we're going to be doing along the way. And so what I'd like to do now is kind of share three kind of vignettes of the types of research we'll be doing. And the first will kind of get at the question I asked earlier, kind of what has marine conservation achieved. Then we'll talk a little bit about what actually is sustainable and some of the progress we're making on defining that. And then I'll scare you guys a little bit of a story. So one of the problems that we have in trying to determine whether marine conservation or what marine conservation has actually achieved is that we actually use the wrong metrics, right? You'll often hear a marine conservation success touted because more area was declared as a protected area. Right? What we often do is tally the amount of area under protection and call that our metric of success. Now, quite frankly, that's just asinine, right? Because there can be such variability in outcomes, right? Those variability in outcomes can be because of the type of management you've implemented, right? More strict types of management may have better outcomes, right? The social and ecological conditions might be more favorable to promoting ecological processes, right? And also, many reefs or many protected areas are extremely poorly complied with, right? So just declaring a lot of areas doesn't mean you've actually done anything except use some paper. So there's been a move towards impact analysis in conservation science, right? But there are practical and ethical considerations that limit the the successful use of what we would often consider the gold standard, which is the use of randomized control trials, right? And you can imagine it's terribly unethical to kind of randomly assign extremely poor people to have very intensive conservation interventions which limit their ability to access food for them and their children, right? Just to see what happens, right? That's quite morally bankrupt, right? So what we're often left to do is use what economists often rely on, but it's like the poor cousin of randomized control trials, and that's natural experiments. Well, I'm going to highlight an approach which I would consider the poor cousin of the poor cousin. And what we're going to do is we're going to engage in counterfactual thinking, right? We're going to do it like a natural experiment, but we're going to use models to predict the counterfactual rather than actual counterfactuals there. And so what we're going to do is we're going to estimate what would likely have happened in the absence of conservation. So this is a project led by Ian. And Ian and I and some other collaborators got a range of scientists from around the world to contribute their reef fish biomass data. Now, on this map, this is a map of the study sites that are included in this. And there's two things that I want you to take home from that. And one is that the bubble size is different. That bubble size is scaled to the, not to the lights, that's really good. The bubble size is scaled to the amount of fish on the reefs. Right, so the bigger the bubble, the more fish there is. But it's also the color of those is based on the types of management. And this is going to come into play a little bit later, right? So the gold ones are sites that are open to fishing, right? That's where it's basically open slather and you can kind of do what you want fishing wise. The green ones are areas where fishing is restricted, right? So maybe spear guns are banned or certain types of nets are banned, right? So there's a restriction, but people can still go fishing there, right? Then we've got our categories, the blue ones are all places that are what we call fully protected marine reserves. These are areas where, at least in theory, you're not allowed to go fishing there, right? But we broke those down into three different groups, right? Those that we used expert opinion to classify the compliance levels. So the light blue ones are those that are poorly complied with, right? So people that live and work in this area have said, no, it's actually, it is what we call a paper park. It's a park on paper, but in practice, people still go fishing there consistently, right? Then we broke down the ones that are high compliance into two categories. The dark blue is the gold standard, right? These are ones that are large, a minimum of 10 square kilometers. And a number of studies have said that's kind of the minimum area where some key ecological processes can occur on coral reefs. So these are large and they're old. They're greater than 10 years old, which has allowed kind of some ecological processes to recover in there. So these are the gold standards that are large and old, right? The medium blue ones are those that they might be very large protected areas, but they're brand new, right? So they don't meet that criteria, or they might be old, but they're really small, or they might be small and new, right? So that's kind of the medium blue is kind of a grab bag of those others. So we then developed a predictive model to predict the amount of biomass on a reef, right? And this is based on social and environmental and management conditions there. Now, there's three things I want you to take home from this first model. And the first is one of the stronger predictors of reef fish biomass was this metric of gravity. And we use two gravity metrics there. One is called market gravity, and the other one we're calling nearest settlement gravity. Now, gravity is a concept that's been used in economic geography for well over 100 years, right? And it's often been used to predict trade and migration flows between cities and between countries. And it's often called the most successful model in economics, right? And so what we did is we kind of adapted this approach to look at what we call the gravitational pull of a market or a local human settlement on a reef to kind of measure the amount of impact. Now, the thing that's relevant, and I kind of want to plant the seed here now, because we're going to come back to it later, is the way that it's calculated is similar to Newton's gravity, right? It's kind of mass divided by distance squared, and mass in this case is the population. And the way that we did distance squared, we didn't just do it as the crow flies, because that's pretty unhelpful unless you're a crow, right? We actually kind of we used land cover data and road networks to map we kind of, you can think about it, it was before Google Maps was really on the scene, but we kind of Google Maps it, right? We looked at the least cost route between the place we were interested in and the reef. And then we calculated the travel time between those. And so we squared that travel time. So it's the population divided by the travel time squared. And so that's going to come back into play a little bit later. The two other things that are interesting, I think, is that we were able to control for human decisions, right? People have different methodologies that they use in sampling fish, so we were able to control for that. We were able to control for some of the other decisions they made, right? Maybe they went over there, which is one habitat type, instead of right there, which is a slightly different one. So we were able to kind of standardize that. The map that you see above, those biomass values, the scaled ones, they're standardized, right? So we've kind of taken the human decision-making that can really heavily influence the biomass values out of it. It's the marginal values. Now, the second thing, though, is because we know the effect on average of management, we can then simulate different types of management. And this is a little bit not straightforward because there is a significant interaction in there. Now, what I want to do to kind of answer this question, what's conservation achieved, is I'm going to show you a figure, but it's going to take me a second to build up. Now, the key thing that you have to know is that for each type of management, there's a distribution of outcomes based on the environmental and the kind of socioeconomic conditions, right? So we've got a distribution. If we then plot each of those sites from the highest to the lowest, we get what's called the cumulative frequency curve, right? So the highest values are plotted first, those contribute the most to biomass, and then the ones that don't contribute much are plotted at the end. So it kind of peters out a little bit. We can do that for sites that are open to fishing. We can then stack on top of those the ones that are restricted fishing. We can then stack on top of those the low compliance marine reserves. We can see that those don't go up very much because they're poorly complied with. And then we can stack on top of those the high compliance marine reserves, and they kind of shoot up. And we can think about that as our status quo, right? The y-axis is the cumulative amount of biomass, right? And it's scaled to 100 because that's how much fish there is now, right? What we can then do is run a simulation. We can create a scenario where what we've done is we've said, well, what would we expect there to be if everything was fished, right? It's an extreme scenario, but there's no management at all, right? And so we were able to kind of simulate for each specific location based on the social and environmental conditions there, what would we expect there to be in the absence of management. And the difference in the kind of cumulative fish biomass between what's been realized and what there would be in the absence of management is what I call the realized gains. Now, the realized gains in this case were about 20%. Did anyone guess kind of around 20%? So I would have, personally, I would have thought it was about 20%. You're right if you didn't think it was 20%, because that's actually an overestimate. And that's because the ecologists that contributed data tended, maybe it's because of funding or because it's prettier there, but they tended to oversample in marine reserves relative to their global distribution, right? So about 25% of our data were from these no-take, these fully protected marine reserves, when in fact only about 3% of the world's coral reefs are from are in these. So what we were able to do was resample the data to get back down to that 3%. And what we found then was about 1 out of 10, about 10%. So one out of every 10 kilograms of fish on reefs is from kind of conservation or management, right? Now, there was a couple of kind of hurdles we had to go to convince ourselves that this might be accurate. And the first was this notion of spillover, right? Now, spillover occurs when a fish from a protected area swims across that boundary, right, and is able to be caught outside of there, or may just swim out there because there's a lot of competition because there's a lot more fish in there, and there may be less competition out there, right? And so what would happen, though, is that the difference between protected areas and fished areas would actually be less. So we would underestimate the effects of protection if there was spillover. Now, conversely, there's something called displacement. Displacement occurs when you add a protected area somewhere, but you don't remove that same proportion of fishing effort, right? So what you then get is 100% of the fishing effort in less of the space. And what that can do is degrade those fisheries further. So what that would do in our model was it would increase the difference between fished and protected areas. It would increase that, and it calls us to overestimate the effects of protection. And so what we did to see whether either spillover or displacement were biasing our results was we ran our residuals through the distance between each site and the nearest protected area. And at least at the scale at which we saw that these phenomena are been reported to occur, we did not see any relationship at all. So this doesn't mean that we don't think that there was spillover or displacement. What it means is that it wasn't really biasing our results. Now, interestingly, one of the reviewers, who is one of the world's best, he signed it, so I can say, he was one of the world's best fisheries scientists and kind of hates conservation, grappled onto this and said this needs to be the central feature of our paper, and we're not doing that because this is a lightning rod, and our data weren't actually designed to test spillover. They could only test whether it was biasing our results. But he loved this story that there's no spillover from marine reserves, and anyway, we'll see how that goes. So understanding what has been achieved not only relies on kind of understanding that one counterfactual of what there would have been in the absence of fishing, but it also requires benchmarking that against what is the scope for potential further gains, right? And so what I want to do, I'm just going to bend your brain here for a second in order to do this. And so that's but on the top right is the figure that I just showed you before, right? And so what I want you to do is now take that curve that we showed you, which is the realized gains, that's the status quo, right? And I want you to take that status quo and then put that just on the x-axis, right? So that's 0, right? We're at the status quo. And then if we take a look at the fish scenario, right, that will then be below that, right? So there's less fish than 0 because it's below that. Well, what we then did was create an alternative scenario, right? Where we said, what if everything was in the kind of gold standard, big and large, big and old marine protected areas? What might we expect? What would be the counterfactual of that? Now, I want to be very explicit that this should not be a policy goal, right? This would be economically, culturally, and nutritionally devastating for coastal communities. So I'm not advocating that this is something worth pursuing, but it kind of helps us judge kind of on a yardstick. Really, it can gauge the status along this gradient from what it would be if it was fully fished to fully unfished. And what we would kind of see is what I would call the potential gains are about 78% more fish biomass than what we have now if everything were fully closed, right? So that's the kind of scope. This is the yardstick in which conservation could actually happen. It can't go beyond that. There's nothing else you can really do beyond that. So what this can also help do, though, in looking at this kind of alternate scenario of everything being protected, is can help us identify sites that would benefit most from protection, right? And so if we just haphazardly assign sites, they would just kind of go in that diagonal line, right? But because we've stacked them from the most to the least in terms of these what we call potential gains, what we can do is look at the difference. And so the difference between, if we take that policy goal of everything being protected, of 30% of the area being protected, and that's what's happened on the Great Barrier Reef Marine Park, 30% of all habitat types are under no fishing zones, right? So if we took that same goal, what would happen is, if we just haphazardly assign sites versus strategically selecting sites, we get about 50% more fish biomass by strategically selecting sites, right? And these strategically selecting sites, these are ones that give you the best bang for your buck, right? And these are ones that have kind of lower market gravity. They've got lower max chlorophyll and lower sea surface temperature skewedness, and a few other environmental and social conditions that I won't go into. But one of the things that I really wanted to emphasize that's pretty cool is, it's a little hard to see. These are all different colors, and because they're stacked against each other, it's hard to see. But a great number of sites are actually in these low compliance areas, right? And this is really important, because what that tells you is we've actually done a pretty good job of siting marine reserves in places that would give you good ecological returns. What we've been poor at doing is managing them well, right? And so there's a lot of conservation gains that can be made, not by declaring new protected areas, even those get wonderful headlines for governments and for conservation groups, right? But what we could actually do if we were interested in measuring outcomes rather than inputs, we could actually focus on improving compliance. Now, I haven't so far talked very much about social science as a social scientist, so I want to turn to that for just a moment and talk about some of the work that I'm doing in collaboration with my PhD student, Stuart, who's currently based in Townsville, may come join us here in a little bit. Now, Stuart is playing experimental economic games with fishers in Townsville. Now these games, and so there's actually skin in the game. Fishers can walk away with 50 or 60 bucks, right, from the game. So there actually is incentives to play the game in a real way that you might. And what fishers can do is they can choose whether to fish in sites that are open to fishing, legal, no problem, payoff is a bit low, or they could fish in what's called the green zones, but these are in the fully protected marine reserves. Now, the payoff is greater, but there's also a chance that you'll get caught and your stuff will get confiscated. And so one of the real fun things that we're doing in this is we're looking at the role of norms in influencing people's decisions. And particularly, we're using what's called the descriptive norm, what other people are doing. And so we're able to actually, in the game, have these computer confederates. These are other players that we're controlling, but they don't know that we're controlling. And we can get them to do different things. So they can fish in the open fishing zones, they can fish in the no fishing zones, we can mix it up, right? And so one of the most interesting things that's come out of Stuart's work is the biggest influence on fishers' behavior isn't from a high compliance descriptive norm or a low compliance descriptive norm, but it's what we call a dynamic norm. It's people respond when they see that norm changing throughout the game, people's behavior changes. And so this is kind of a really interesting result from preliminary result from his work so far. All right, so on to the second vignette. So what, right? What does it mean if there's 10% more fish on reefs than there would be without conservation? Does that mean it's sustainable, right? So 10%, an increase of 10% could go from unsustainable to unsustainable, and it may not matter, right? Or it could go from sustainable to sustainable, and again, not matter. It's kind of, it's at that margin when things go from unsustainable to sustainable that you get the biggest gains. Well, there's a lot of data out there, but we lack what's called reference points, sustainability reference points, to know what the assessments mean. We don't know how much fish on a reef is a sustainable amount of fish on a reef. So saying that biomass is declining is completely useless. It's how long is a piece of string? You're only saying that there's less of something, but you're not saying whether that amount is meaningful, right? We can't assign meanings to trends unless we understand where these reference points, whether the trends are in relation to reference points. Now, this is particularly hard in coral reef fisheries because they are exceptionally multi-species. My work in Papua New Guinea revealed that there are 169 different species caught by spear guns alone. And people also use nets. People also use harpoons and hook and line, each of which captures a different suite of species. So you're dealing with hundreds and hundreds and hundreds of species that are being captured in this fishery. Now, conventional fisheries management can deal with multi-species things with like 3 different species, right? So what we're dealing with in coral reef fisheries is just beyond the scope of what conventional fisheries management models and assessments can even do. So we've been trying to think of what are other ways that we can approach this problem. And about 10 years ago, we kind of started down this line of inquiry with a colleague of mine, Aaron McNeil. And what Aaron was able to do, he's kind of a Bayesian Jedi master, is the way that I would put it. And so what he was able to do is look at, we treated the stock as we treated the entire assemblage as a single stock, right? So all of the coral reef fisheries, all the coral reef fish, we treated as a single stock. And the way that we looked at the recovery was tracing how marine reserves recovered over time and in asymptotes. And the problem with it as an asymptote is that it can go on for infinity, right? It kind of creeps up and creeps up and creeps up forever. So how do you anchor that? Where do you stop that from going? So what Aaron had the idea of doing was anchoring it using really remote reefs that are 20, 30, 40, 50 hours away from people, that are very rarely, if ever, fished, and saying, well, that's how we could anchor the amount of fish there. So we were able to calculate, in ecology, what's known as R, right, the recovery curve. We were able to calculate the recovery rate for the entire assemblage of it. And this led to us creating what's called a foundational reference point. This is what's called unfished biomass. That's the amount of fish you would expect in the absence of fishing. But it had low uptake in terms of fisheries management because we were looking at a global average, right? So we were able to calculate, on average, 1,000 kilograms per hectare is how much fish you would expect there to be in the absence of fishing. Well, I think reef fisheries managers are maybe a lot like parents, and they never want to have an average child or an average reef, right? So nobody really, this didn't get as much traction as we would have kind of hoped because it wasn't site specific. So along came our superstar PhD student, Jessica, who's now gone on to do her postdoc at Harvard. And she published a paper last year which really cracked the code on this. Jessica was able to estimate these foundational reference points by incorporating a whole range of social and environmental conditions on there, which allowed us to now develop locally specific, kind of bespoke sustainability reference points. Right? And this is something that I think fisheries managers will be much more keen to use. But there's a few little problems with those. And this is where I think there's a lot of room for my group to be working and collaborating with others on. This is really where one of the areas that I'm very excited about. Now, one of the things that you do when you calculate this unfished biomass reference point is you can use different aggregate biomass dynamic models to calculate how much fish there should be on a reef before it's unsustainable. This is the biomass at multi-species maximum sustainable yield, right? And there's different competing models that do this. Now, the challenge that we had, right, was that we were able to select a best model, but it wasn't a whole lot better than the other models. And that has really profound implications. Let me just show you what I mean by that. So the most conservative model, right, the median posterior distribution of that is around 70 tons per kilometer squared. And kind of above that, it would be considered sustainable. So if you're fishing it, if your biomass is at 72 or 75 tons per kilometer squared, it would be sustainable. And below that, you're beginning to get overfished, right? Well, the model that ours kind of settled on was this least conservative model, right? And what this kind of says is it's about 35 kilograms per hectare is the median posterior distribution there. So the difference is one model can be considered sustainable at about half the biomass as another model is sustainable. So my concern is that we could be making policy prescriptions to people saying that it's sustainable when it's not, right? And so what I'm really excited about doing is throwing a lot more data at this to really better understand when these different aggregate biomass models might be appropriate, when we might get different types of recovery curves in the biomass, what types of local, social, and environmental conditions might be doing that. As I mentioned, we've got kind of 26,000 sites from 68 different countries. We're partnering with the top groups in the world. We've got the United Nations Food and Agriculture Organization. We've got a development organization called WorldFish. We're partnering with the Wildlife Conservation Society, which is one of the world's largest environmental NGOs, and with state government agencies here in Australia as well. And what I'm most keen to do with this is develop a decision support tool to provide kind of real-time status and trends, to create downscaled estimates that are relevant at the scales at which people are making decisions, and to allow them to kind of estimate some of the trade-offs to inform how they might be able to achieve some of the key goals that they want to do and what are the costs of doing so. All right. Now, I want to wrap up here with a little bit of a ghost story. And this is based on some work that was just published a couple of weeks ago led by a PhD student in James Cook University, Jaden Enger. And what we did in this paper, and when I say we, I definitely wasn't involved in this part of it, is traced thousands and thousands and thousands and thousands of satellite images and traced the roads on those, right? And what we then did was we compared the actual roads based on satellite data to roads that are in publicly available data sets. So there's two key global data sets that planning departments and scientists constantly use. One is called GRIP and the other one's called OSM. OSM is OpenStreetMaps, right? And so what we did is we compared the amount of roads in the 3 largest islands in Southeast Asia. And what we found was there are between 3 and 6.6 times more roads than is revealed in these kind of open source road data sets. And again, these are being used for planning, for conservation, and so it has a lot of implications. Now, there's 3 key results from this. And one is that road density was the strongest predictor of forest loss, right? And it was way more so when we used these, what we call ghost roads, right? The ghost road data set. And so when we created a model, it had the strongest effect size was from this road density. And what I've then put up there is the exact same structure of the model, but we're using a different road data set. And what we can see is the effect of roads is a lot lower in this other one. And the same when we use the other road data set there. So what is happening is that by using these globally available data, we're underestimating the effect of roads, right? The second thing that was interesting from this study is that, it's kind of a good news story here a little bit, is that there's actually far fewer roads, about half the amount of roads in protected areas compared to outside of protected areas. Now, this is after having accounted for the fact that most protected areas are located in places that you wouldn't put roads in anyway, right? They're up steep mountains or they're in swamps, right? But what we were able to do was we were able to match pixels in protected areas with similar environmental conditions, slope, rainfall, water flow, that sort of stuff. We were able to match those. So given other things being equal, there was still less roads in protected areas. So protected areas are doing a good job of keeping roads out. So that's kind of cool. The thing that really surprised me though, was that once we accounted for the fact that there was lower roads in protected areas were having almost no additional impact on forest loss. So the main role of protected areas in these regions, at least for forest loss, is the role in keeping roads out. They're not doing a whole lot else beyond that, and that was kind of surprising to me. Okay, so the last thing that I want to touch upon with this is that there's a number of kind of human impact metrics that are used by conservation groups and planning departments that are based on these global road networks, right? And probably the most popular one is called the Human Footprint Index. And what we did is we compared the Human Footprint Index for that little corner of Borneo there. We compared the Human Footprint Index based on its original calculation, and then we compared it with our ghost roads data set. And what you can see is we're severely underestimating the kind of human footprint when we use these globally available roads data. Now, I planted this seed earlier because I wanted to kind of circle back to it now. Now, I'm guilty of doing this too. So one of the great things about this paper for me was realizing kind of what I need to start doing in my own data, because we've been calculating this gravity metric using globally available roads data. Right? And what is clear to me is that we need to really up our game. And I think one avenue one fruitful avenue will be using AI to calculate, to kind of trace roads from satellite images, right? Because it's too much to do it globally by hand. You know, that was like 60,000 hours or something like that to trace for those 3 islands there. We can't possibly trace it by hand for the world. So we need to start kind of automating that. And so I think a real exciting approach will be using AI to kind of trace the roads in these areas that are kind of near coral reefs and start integrating that into our gravity metrics. So I think this is an area, if you guys have the skills and want to collaborate, this is a great area to do that on. So with that, I would just like to say thank you very much for having me. It was a pleasure chatting with you guys all, and I thought maybe I would just go back and see what we found there. Yeah, so I mean, a couple people got it. I think that's all. I think those are right within the bounds there. I think that's pretty good. A lot of people are very pessimistic about what conservation did, right? A lot of people, the most that, yeah, wow. All right, there you go. So anyway, with that, I'd love to take some questions if you have any.
Let's clap first.
Great, well, thank you, Josh, for your very engaging and very interesting presentation. So we've got about 10 minutes left, so we might jump first to some questions in the room. If anyone on the Zoom has questions, maybe just pop them in the chat and we'll monitor that just while we wait for you guys to type them through. So we'll jump between Zoom and in-person questions. Yes.
Thank you. I'm not asking a tropical forest question, obviously the 5% of your talk. I was just wondering that finding about roads and deforestation is really interesting. Is there any way that you can look at interrelationships between protected areas and diversity and roads, like using satellite? Because in Asia, obviously, forest is probably the dominant land cover type in non-urban areas. So can you look at diversity at all in that? Because well,
I think this is a great idea. You know, what we did was look at forest loss over time, right? And so we just looked at the kind of conversion. Can you get diversity metrics from satellite images?
That's why I'm asking you, because I just worry that kind of finding would dismiss the role of protected areas in diversity protection.
Yeah, totally. And that's why I said using the metric that we did. So I totally agree that, you know, there may be, and you know, that didn't touch on the host of social and economic benefits that protected areas might have as well. That was just solely focused on forest loss. The main role seems to be keeping out roads. But again, yeah, that surprised me. But that doesn't mean that that's the only thing that protected areas do, right? And so this is where we get it kind of, you know, anytime you're using a unidimensional measure of success, you're going to run into these problems.
I do wonder how much pixel diversity in really high quality satellite images might be able to start moving into diversity prediction.
Yeah, I think probably. Right. I think Mitchie had the next one. Yep.
I was just going to ask, with when looking at like baseline sustainability in the reefs, how far back are you starting? Because when you start looking at something, it's like saying restoration. When we want to restore something, at what point are we wanting to restore it? What to? And so the sustainability kind of metric then changes when you're looking at something extremely long ago compared to 20 years ago.
Yeah. This is an awesome aspect here, Mitch. And so what we are referring it to when we looked at that, what we would call potential gains, right? Where we struggled was, do we do potential gains where, you know, because in the model you can move various things, you can run scenarios. And so our scenario was leaving gravity, this metric of human impact, where it is, but changing management. And one of the things we discussed is that the right approach? Is the other approach that we actually take gravity down to zero, right? Where what you're really saying is, what is the projected, you know, what might there be in the absence of humans and with good management, right? And so what we decided to do in this particular paper was focused on what we kind of termed to ourselves pragmatic conservation gains. These are ones that you could achieve in the current social and environmental conditions, rather than things like, you know, mass genocide where you're removing people from the system. But you know, so I love the work of historical ecologists, particularly in reef studies, and really, you know, they've got these amazing pictures of, you know, people trophy hunting reef fish this big when, you go back 50 years and they're up to the ceiling of the same species of fish. And I think your point is really well taken that, well, we get this kind of shifting baseline, and we specifically wanted to keep it with what we call these pragmatic conservation gains.
Because even with, if we were to talk about, let's say through Australia with Indigenous interactions, a lot of Indigenous methodologies promoted sustainability and promoted growth and everything. So if there was taking all human interaction out, would change that as well. And so there's a dynamic that needs to be, I guess, understood between what is a beneficial interaction and what isn't, and how that interacts with those environments.
Yeah, and I think this is a really exciting avenue to kind of start thinking through some of the difference between land use change philosophies and sea use change philosophies, because in things like clam gardens, you are able to see these things where people can construct the system in such that they can then increase the habitat and benefit biodiversity. It's slightly different in wild capture fisheries. Mostly what you do in wild capture fisheries is kill fish, right? And so I'm more comfortable with that approach in wild capture fisheries than I would be in things like shellfish. Oh, yeah. Anna.
Hey, so I'm going to ask a social science question because I'm a social scientist. Are you thinking about, in terms of this, economic sustainability picture, and it's related to Mitch's question, are you thinking about industrial capitalist fisheries versus self-sustaining communities? When you're talking about market gravity, that's just the local place as opposed to the giant markets all across. How are you factoring in the possibility that in a single place, political ecology, you'll have a myriad different processes going on, whether it be some subsistence fishes, there'll be some giant sealord operations, blah, blah, blah. How does that get woven into the story that you're telling? So
the thing about global scale studies is that they are a global disappointment. They're the most disappointing thing you'll ever do, because all of these interesting things that you so want to delve into, you simply can't, right? Because what I would love is a global database of every place that coral reef fish are sold and the proportion of those that go to subsistence versus markets, right? That doesn't exist at all, right?
Just fishing for subsistence or fishing for capitalist markets, which imply a certain relationship with the area being fished.
Right. And interestingly, most coral reef fishers do both simultaneously, right? So they will go fishing, sell the most marketable stuff, and subsist on the least marketable stuff, right? And that can change over time as preferences emerge. And so, it's not a binary thing in there at all. And so, the best answer that I can give to you in that is that the global scale part of the study simply can't address that. But where we get into that is really when we go in and do that targeted field work, And so one of the things I'd really like to be looking at is kind of supply chains and the kind of networks that are there that kind of link people to the capitalist markets,
Yeah.
And again, so reef fisheries is pretty different from a lot of other fisheries because it's normally not high value enough to go that far, right? So, and it doesn't, they're small fish, so they don't, they dry okay, but not great. Their value isn't great dried. And you compare that with something like shark fins, which are, worth a fortune, and beach demare, which are sea cucumbers, they're literally worth more than gold, right? And so reef fisheries aren't worth that much, but they're really important for people's nutrition, right? And so a lot of times they're in these kind of hybrid, they're what I call artisanal fisheries, which are neither subsistence nor commercial, right? They are both.
Thank you.
Right, so just keeping an eye on time, we haven't had any questions come through over the Zoom, but we're just on 2:00. So thank you all for the questions, but I might just wrap up the session for today. So thank you again, Josh.
Welcome.
Thank you.
I'm really interested to see what you and the new team find out with all your really interesting research. I will just highlight that the next fortnight, so May 8th, we'll have our next Thinking Space session. So Dr. Billy Hayworth will be presenting his research on disasters and vulnerability. So I hope to see you there for that session too. Thank you, everyone.
Thank you.